Hello, everyone. Let's dive into a quick overview of Unit 4. In Unit 4, we'll be implementing a real-world design. This design is focused on a Multiport Virtual FIFO DDR memory controller. This type of design is commonly used in applications like multi-channel image transmission and reception, as well as multi-channel network packet transmission and reception. It's a widely applied design in these scenarios. We'll provide the complete source code for this design, starting with the block diagram explanations and the design system Verilog/Verilog RTL modules, along with the Synthesizable testbench. We'll cover all these aspects step by step, providing detailed explanations and analysis. Our goal is to help you truly understand how to apply this design in practical circuits. This unit is divided into 4 subsections, with 4 to 4 as an appended design debugging session, which shows how to use Vivado Internal Logic Analyzer IP. Section 4 to 1 starts with learning about the DDR memory IP and its core functionality, as well as gaining a foundational understanding of DDR memory. The key is to get familiar with this IP, so we can use it effectively in hands-on exercises. This IP is part of the Vivado, the FPGA development toolset. We'll also select a specific circuit board to perform actual synthesis implementation and real hardware testing. In Section 4 to 1, we have 3 smaller labs. The first lab involves using the tool Memory Interface Generator MIG to create and configure the DDR memory IP matched with the hardware board. During this process, you'll need to configure some settings. Then we'll open an example RTL design which generated by MIG automatically. That also includes a fully synthesizable testbench. We'll use this to walk through the example, as its testbench is very well written, making it easy for you to understand what a synthesizable testbench looks like. It also includes automated comparison features. Through this example, you'll learn how experts write designs and their corresponding testbenches. In Lab 412, compared to the previous lab, this lab enables an advanced PRBS test pattern in the testbench. PRBS stands for pseudorandom binary sequence. We'll explain PRBS in more detail later, but simply put, compared to the previous lab, this test pattern is relatively simple. In this lab, the pattern is more complex, making it easier to identify functional issues in the memory through write, read, and compare operations. This helps detect data errors more effectively. Lab 413 focuses on the testbench, which includes different options that, when enabled, allow you to calculate read and write efficiency. Through Labs 411, 412, and 413, you'll become familiar with the memory IP and learn how to write a synthesizable testbench, as well as evaluate its performance. Section 4 to 2 is the centerpiece of this unit, focusing on our real design, the Multiport Virtual FIFO DDR memory controller. We'll dive deep into the desync architecture, how to implement this design, and how to write its testbench. This multi-channel Virtual FIFO, as mentioned earlier, is frequently used in multi-channel image streaming and multi-channel packet transmission and reception. It's a critical component in these types of designs. Section 4 to 3 builds on the design from 4 to 2, where we perform the design logic, synthesis, and implementation. You'll learn about the circuits, timing, area, and power characteristics. Back to 4 to 1 as we discussed. After understanding the basics of DDR SDRAM and its controller, we'll work with the specific DDR DIMM type used on the chosen circuit board. Based on this, we'll configure the IP to match the board's DDR type. Once the IP is set up, we will generate the memory controller IP, its example RTL design, and synthesizable test bench. Using this example, we'll start running simulations and then perform logic synthesis and implementation. As mentioned earlier, Lab 411 introduces the structure of the memory IP and the synthesizable test bench. This simple test bench essentially writes data in a linear sequence like incrementing by 1, then reads it back for comparison. It uses a straightforward test pattern. In Lab 412, we introduce an advanced test pattern called PRBS, which stands for pseudorandom binary sequence, which is commonly used to simulate random data patterns and detect faults. In simple terms, this test pattern generates data in a near-random manner to write to the memory, then reads it back for comparison. It's called pseudorandom because it follows an algorithm, which is commonly covered in digital logic testing courses. You'll likely encounter this testing technique in such courses. This advanced test pattern is also synthesizable, and we'll study its structure and how its code is written. Before running simulations, Lab 413 focuses on calculating the performance of the memory controller, since the test bench includes both write and read operations. For example, if you have 100 writes and 100 reads, or 1000 writes and 1000 reads, you can measure the number of write and read operations and how many clock cycles they take. This allows you to calculate the overall efficiency of the design. As we mentioned, Section 4-2 is the main focus, covering the multiport Virtual FIFO. The design can be broken down into several key components. First, you need to partition the memory into n spaces, where each space is independent and doesn't interfere with the others. Each of these n spaces is treated as a virtual FIFO, which is where the term Virtual FIFO comes from. This setup requires addressing several challenges. For instance, if you have n channels for the FIFO, you'll have n instances, each operating with asynchronous clocks. This includes the FIFO's write clock, read clock, and the memory clock. With n channels, you'll have n write clocks and read clocks, and one memory clock, the memory clock. Because each module may have different clock, you must handle asynchronous operations between all the modules. We'll cover asynchronous handling in detail. Note, in digital logic design, reset synchronization must also be considered, not just for clocks and data. You'll need an asynchronous FIFO to manage clock domain crossing, CDC. Again, resets require careful synchronization. Another important aspect is the data width of the FIFO versus the memory controller's data width. These widths are different, and we'll explain why. This difference arises because DDR operates at very high speeds. For example, if DDR4 data rate is 2400 megabits per second, meaning the I/O would need to run at 1200 megahertz, where the clock rate is data rate divided by 2. Running a 1200 megahertz clock inside the logic is impractical, so we typically reduce the clock speed further, say by dividing data rate by 4 to 300 megahertz. When you lower the clock frequency, the data width must increase to maintain the same throughput. Thus, the internal data width becomes larger. For example, data width of user module is usually with 32-bit or 64-bit, but the memory controller might use hundreds of bits, like 576 bits in data path. This requires a width conversion. Another key point is that, with multiple channels, you need a fair arbitration mechanism to manage access request from all channels. This arbitration ensures only one channel access the memory at any given time, since there's only one memory and one controller. We'll demonstrate how to write an arbiter. For the round-robin arbiter, we are using a finite state machine approach, ensuring the fair arbitration. This is a core part of the multiport virtual FIFO design. Let's talk about the virtual FIFO interface itself. Why is it called a virtual FIFO? Because FIFO stands for first in, first out, and its interface is quite simple. Data is written on one end, and read from the other end. It's a straightforward interface. For example, when writing data, you set the write signal, WR, from 0 to 1, then input the data through the data in port, DIN. Of course, you first check the write ready signal, WR_ready, to ensure the FIFO has enough space to write. Only then can you proceed. The same applies to reading. When reading, you check the read ready signal, RD_ready, to confirm there's enough data to read. If the RD_ready signal indicates data is available, you can read the data by initiating the read operation. To read, you set the read signal read from 0 to 1, depending on the FIFO logic design. After 1 or 2 or more clock cycles, the data appears on the output. That's roughly how it works. Looking at the waveform, when the read signal goes from 0 to 1, the data output appears after 1 clock cycle. That's the behavior. Alright, let's look at the block diagram, since the block diagram is critical for any design and must be drawn first. As you can see, this is an example. Our design uses 10 channels, but it can scale to n channels without issue. On the left, the green box represents the multiport virtual FIFO itself. Each small blue box is an individual virtual FIFO. The arbiter manages these virtual FIFOs. As we discussed, each virtual FIFO handles tasks like asynchronous processing, such as during writes, and data width conversion. For example, user data might be 64 bits, but the memory controller data path is 576 bits. So, 64 bits times 9 equals 576 bits, requiring a 1 to 9 conversion. You need to collect 9 64-bit data chunks to write to the memory. That's what we discussed earlier. Reading works similarly, where 576 bits are converted back to 64 bits, a 9 to 1 conversion, outputting 9 64-bit chunks. That's for reading. Additionally, as we mentioned, data in and out requires asynchronous FIFO handling and width conversion. Next, you need to implement arbitration, which operates on 2 levels. The first level is within each FIFO, handling write and read requests. Note, both write and read may request access permission to the bus. Only after gaining bus ownership can the FIFO read or write through the DDR memory controller. This is the first level arbitration, deciding between write and read within each FIFO. After this, the FIFOs may request the second level arbitration, which occurs outside the FIFOs. Here, all 10 channels may compete for bus ownership. Once a channel gains access, its corresponding virtual FIFO can perform read or write operations. That's the concept. So we have first level and second level arbitration. First level arbitration happens inside each virtual FIFO, managing write versus read requests. Second-level arbitration occurs outside the FIFOs, where the 10 FIFO channels compete. That's how it works. We'll cover this in more detail in the course. For now, we won't go too deep, as we've already touched on the basics. The Virtual FIFO handles multiple tasks, including the synchronization. As mentioned, the asynchronous FIFO, which is an IP, will show you how to use it. The 10-channel round-robin arbiter is a design often tested in job interviews. There are other ways to design an arbiter, not necessarily using a finite state machine. You could use alternative approaches, but we chose the state machine method because it's intuitive, simple to explain, and less prone to errors. Each approach has its pros and cons. We also mentioned reset synchronization, which is critical and applies to all designs. The top-level multiport Virtual FIFO is written in system Verilog. Why? Because in this design, we will instantiate 10 channels, and each channel's input and output ports are more than 1 bit wide. With 10 channels, you need two-dimensional input and output ports, or internal data buses. It's easier to use system Verilog to define two-dimensional variables in RTL modules, including all instances and bus connections. Let's revisit the Synthesizable testbench. The green box represents the testbench itself, designed to test our multiport Virtual FIFO. The DDR memory controller is not part of our design. It's an IP. We only interface with it. That's why it's not included in the green box. This is our multiport Virtual FIFO design. The testbench includes 10 test data generators, performing write operations, and 10 FIFO pop operations for reading and comparing data. The data generation, or FIFO push, continuously writes data into the FIFO, while the compare read or FIFO pop reads data as soon as it's available and compares it. If there's an error during this process, you'll see it. For instance, if the FIFO is full, it indicates an issue, likely causing errors. You can observe this through certain signals. These details will be covered thoroughly in the course. After writing our multiport Virtual FIFO, our next goal is to create a synthesizable testbench. What's the objective? We want a testbench that's synthesizable and performs automated comparisons in both simulation and real hardware testing. As mentioned, we'll implement a FIFO push function that monitors the write-ready signal and generates test patterns. Each Virtual FIFO channel, from 0 to 9, has its own FIFO push. If there's enough space, it continuously generates patterns and writes to the Virtual FIFO from channels 0 to 9. There are 10 FIFO push instances, corresponding to the 10 Virtual FIFOs. Similarly, for reading, FIFO pop operates on channels 0 to 9. Each Virtual FIFO, from 0 to 9, has a corresponding FIFO pop. If data is available, it continuously reads it back and compares it. The testbench knows the expected results, so we have a top-level testbench that integrates all these components to achieve automated comparison. These finer details will be explained in the course. Our example program builds on Section 4 to 1, leveraging the FPGA tool-generated test framework. We adapt it to our own testbench, keeping the outer framework intact. This framework, or shell, includes components like the DDR controller and DDR SDRAM simulation model, which we can reuse. So, we take the Vivado FPGA tool-generated testbench and replace its modules with our own, while keeping the interface. This gives us great design flexibility and saves time. Alright. The basic flow is writing data to the memory controller, then reading it back for comparison. That's the simple flow. Of course, the details are more complex, and we'll cover them later in the sections and labs in depth. You'll see the 10 channels, continuously writing to the Virtual FIFO and reading back. In simple terms, 10 channels perform FIFO push to generate data, writing to their respective virtual FIFOs, and 10 channels perform FIFO pop to read data from their virtual FIFOs and compare it. Finally, section 4 to 3 focuses on implementation, covering synthesis and implementation, since we're using our modified design modules, so must also update the constraint files, including new false paths and additional I/O pin locations, as well as new settings. Based on our modified multiport virtual FIFO, we'll adjust the constraint file, then perform synthesis and implementation. We'll verify that the design meets timing requirements, STA, and fits within the area constraints. You'll review the timing report, area report, and even analyze power reports. You can also examine the design rule check report and other details. This will be covered in Lab 4 to 3 and Section 4 to 3. And Section and Lab 4 to 4 is about using Internal Logic Analyzer IP to debug the RTL logic modules. From above you may see, Unit 4 serves as a comprehensive culmination. Mastering Unit 4 should equip you to handle most digital logic circuit requirements and specifications. All the techniques we've discussed are applied in this unit. We've covered Verilog syntax, like the /generate constructs used to instantiate multiport designs. We also used two-dimensional arrays and buses, which requiring system Verilog syntax. So Unit 4, especially Section 4 to 2, presents a design we created, and we'll explain in detail. This should help you understand digital logic design, or FPGA design, from the basics to advanced concepts. That's the overview of Unit 4. The detailed course content will be revealed in the upcoming sections with in-depth explanations. Thank you all.